G'day. Thanks to the CCA board for the opportunity to discuss the Fertcare Soil Sampling Guide. Intensification of agriculture and fertiliser use has an important part to play in feeding and clothing an ever-increasing world population. There are several examples of nutrients entering waterways and causing algal blooms or other undesirable reactions. Examples include the catchments of the Great Barrier Reef in Queensland, the Peel-Harvey Estuary in Western Australia, and more recently the waterways of the north coast of New South Wales have been identified as having poor water quality. In these examples, fertiliser may be one of a number of factors contributing to eutrophication. Also, the Australian Government plans to reduce greenhouse gas emissions by 26 to 28% on 2005 levels by 2030. Fertiliser use on agricultural land can both positively and negatively impact on greenhouse gas emissions. Clearly, the use of fertilisers and organic soil amendments can have environment and food safety implications which need to be managed in the advice passed on to farmers. So how do we tell if an individual is providing sound advice to farmers? Should it be based on how well the person's known, or if they're a great bloke or a great lady? Should it be based on what educational institution they went to, or what they studied, or who they work for now? Should it be based on the crop yield resulting from the recommendation? Or perhaps the produce quality, or the level of impurities or biological contamination in the end produce? Some in the community would suggest the quality of advice should be based on the wider environmental consequences of the recommendation. The soil and plant nutrition approach that Fertcare endorses is to use objective measures such as soil or plant tissue testing, appropriate analysis and interpretation methods to arrive at evidence-based, site-specific nutrient management plans at a paddock level. The basic premise is to match crop nutrient demand with the nutrients available from the soil, applied fertiliser and other nutrient sources such as animal manures or compost. Minimising the nutrient surplus to crop requirements will significantly reduce the potential for off-site movement of nutrients. It's a simple concept, however, it's a little more challenging to put into practice. So why would evidence-based fertiliser recommendations be a sound basis for agronomists to operate by? Firstly, trust. Trust between your farmer, customer and yourself is built through the ethical provision of advice, which is demonstrated by basing fertiliser advice on objective measures such as soil or plant tissue testing. Secondly, as agriculture and its off-site impacts on water quality and greenhouse gas emissions come under increasing public scrutiny, basing fertiliser recommendations on a body of evidence that can be defended from a science perspective will be one of the factors that help the industry strengthen its social licence to operate. The aim of the Fertcare Accredited Advisor program is to provide farmers and other stakeholders with confidence that farmers are receiving fertiliser advice based on soil or plant tissue testing of a high standard. The program assesses the competence of advisors to make nutrient recommendations. Assessment is based on standards set by ASPAC, which have been mapped to national competencies from the Rural Training Package. The 5 accredited advisor performance standards cover sampling, analysis, interpretation, recommendation and monitoring. Once advisors have been assessed as competent, they are encouraged to display the Fertcare Accredited Advisor logo on their recommendations and personal communication. They are also subject to a biennial audit of randomly selected recommendations they've made in the preceding 2 years. Collecting soil samples which accurately reflect the plant root zone is fundamental to evidence-based fertiliser recommendations. We have to get this part of the process right. Cameron will now unpack some of the Fertcare Soil Sampling Guide.
There's a few key principles and practices that I wanted to highlight today. These are pretty straightforward and logical, but I guess it's surprising how often we ignore their importance just to get the job done. So first of all, I wanted to address what makes an accurate soil sample. So I would define an accurate soil sample as a collection of soil that represents the soil rooting environment of a crop or pasture being investigated. So for example, if we take a 10 hectare paddock, there's around 10,000 tonnes of soil in the top 10 centimetres. And we routinely collect about 2 to 3 kilograms of sample across this paddock when we're collecting a field soil sample. We send off around half a kilogram to the testing laboratory, and ultimately the chemist uses around 10 grams of that sample for chemical analysis. And we rely on these chemical analysis as the basis for fertiliser and soil ameliorate recommendations, costing the farmer many tens of thousands of dollars. So this is why accurately collecting a representative sample with the right number of cores to the right depth is so important. We want this sample to reflect the specific characteristics of the soil root environment which influence plant growth and productivity, such as nutrient supply, nitrogen, phosphorus, potassium, sulphur, or perhaps adverse chemical conditions such as soil pH, aluminium toxicity or sodicity. Maybe physical characteristics such as clay content, water holding capacity. And we should always ensure that the standard Australian testing procedures are used by your testing laboratory, and that these are approved and quality assured by the Australian Soil and Plant Analysis Council. You can then have confidence that soil test results are calibrated for Australian soil and cropping conditions, and that a standard suite of soil tests will provide the combination of the most relevant tests for the cropping system that's being investigated. So when selecting an area to sample, it is important to recognise the source of variability. Across a farm, soils may be highly variable as a result of parent material, clay and organic matter content, topography and drainage, and of course previous soil management such as cropping, tillage history, and previous fertiliser or ameliorant use. The collected and bulk soil samples, which make up a representative sample, should therefore represent, as best as possible, a standardised set of conditions. Don't assume that soil characteristics are consistent within a paddock. Aerial photographs, paddock boundaries, soil types and hydrological characteristics, yield maps, all of these are useful in planning sampling locations. Selected representative paddocks with common characteristics and management, which then make up a larger proportion of the farm, are often annually sampled to monitor changes in nutrient availability and chemical conditions over time. Industry advisors often have a favourite sampling pattern, be it zigzag, transect, random or cluster sampling collection. As long as these are done well, there is often little difference in the results, but in every case it's important to record the exact sampling method and the location and use the same sampling approach between years. So how many cores should be collected? Of course, the answer depends on how accurate you want to be. Paddocks with high spatial variability require more tests. But we rarely know the variability of a paddock before we sample. So we generally have to standardise the number of cores based on an expected variability and sampling core dimension. This detailed graph shows the low and high soil variability as the variability curves increase towards the top right. The x-axis describes the percentage difference from the true paddock value, also defined as an acceptable error. The y-axis tells us how many 19mm cores in this case we will need in a bulk sample. We usually standardise the acceptable error at 15%. So for a paddock with average variability, shown as the defined curve on this graph, we need around 40 19mm cores in the bulk sample. If we're using larger 25mm cores, for example, these will collect a larger volume of soil. So in this case, you need around 30 cores. The variability of soil characteristics is lower in subsurface samples, so you can get away with between 10 and 20 bulk cores when we're sampling our subsoils. The key message here is that you need a minimum of around 30 to 40 cores to make up a bulk sample for our surface soils, less for subsoils. If you want to be more accurate, you need more cores. And finally, how should we sample a paddock with fertiliser bands? Where there's been previous precision placement of fertiliser in a previous season, then particular sampling patterns are recommended. This is because we want to represent the forthcoming root environment, which will include soil with low or no fertiliser contact, as well as soil directly affected by the previous fertiliser band. So as the newly sown crop will be planted between the previous rows, a much greater proportion of cores should be collected between the rows than within the previous row. For a standard row width of 35 centimetres, there should be about 8 to 12 soil cores collected between the rows for every one core collected within the previous row. And if row width is narrower, then take fewer cores between the rows, and if it's wider, then take more cores between the rows. So while there's continued technological development in nutrient management, including things like automated analysis, remote sensing, and enhanced efficiency fertilisers, we must always remember that accurately collecting soil samples is the most important starting point for profitable and sustainable fertiliser use.